Today, I would like to talk about the modeling of periodic microstructured materials using peridynamics. Before we start, here is an outline of this presentation. We will first have a quick look at the peridynamic theory. Then I will present you the ordinary state-based peridynamic homogenization approach with some numerical results. Now, I would like to briefly talk about the peridynamic theory. Peridynamics is a non-local continuum formulation introduced by Dr. Filling. Unlike classical continuum mechanics, the equation of motion in peridynamics does not contain spatial derivatives. Instead, the integral form equation of motion is applied everywhere, regardless of discontinuities. This makes peridynamics very effective when dealing with defects such as cracks and voids. Defect definition in peridynamics is done by simply breaking the bond between two material points, and as a result, multiple cracks can develop and interact with each other in peridynamics naturally without any special treatment. Next, we will have a quick overview of our ordinary state-based peridynamic unit cell homogenization approach. One of the reasons to do homogenization is to transform a difficult problem into an easier one. Running numerical analysis on macroscopic periodic structure directly could easily overwhelm our computational capacity, even for modern supercomputers, when we are facing millions of degrees of freedoms. So instead, we choose to perform a unit cell analysis on a macroscopic structure first. This will provide us with the effective properties of the periodic material, and therefore transform the heterogeneous material, which is difficult to solve, into a homogeneous one, which can be solved quickly on most computer systems nowadays. Here we have a brief review of the periodic boundary condition used in unit cell analysis. Periodic boundary condition is made up of two parts. First part is called the traction boundary condition. It means the traction force at the opposite surface of the unit cell is equal in magnitude and opposite in direction. The second part is called displacement periodic condition. It states that the displacement at opposite surface is equal to the displacement at current surface plus the influence from a strain in the system. There are many ways to impose this periodic boundary condition in peridynamics. Notably, Dr. Madansi from University of Arizona proposed an elegant way of doing it by utilizing the family horizon property of peridynamics. By replacing the family members of those nodes that located at the boundary with other nodes at the opposite side of the cell, we can satisfy the periodic constraint naturally. The homogenization procedure consists of solving 6 separate boundary value problems, that is, 3 for normal strain and 3 for shear strain. For 2D problem, this can be simplified to 2 normal strain and 1 shear strain. For each of those cases, periodic boundary conditions are being applied to the corresponding corner pairs, edge pairs, and surface pairs of the unit cell. Once 6 boundary value problems are being solved, the stress field can be further obtained based on the displacement field. And by volume averaging the stress field, we can assemble the effective material property matrix C star. Periodic boundary condition is sometimes mistaken by some who are not familiar with this topic with homogeneous boundary condition. And homogeneous boundary condition is a different kind of boundary condition which strictly define the displacement at the boundary. However, periodic boundary condition only set a relative position for each boundary pairs, and the exact displacement value is not strictly imposed on any individual node. Now I would like to show you some numerical results from ordinary state-based peridynamic homogenization. For our first example, we will look at the unit cell analysis of a composite cell and compare the result with traditional finite element approach. The center positioned fiber has an elastic modulus of 3E9 Pascal and Poisson ratio of 0.4. Volume fraction of the fiber is also 0.4. Elastic modulus for matrix is 2E9 Pascal, and the Poisson ratio for matrix is 0.3. Since it is a 2D scenario, we performed 3 loading cases following the homogenization procedure we introduced previously. The result is put into comparison with traditional finite element homogenization approach, and we can see the numbers are consistent with each other for both effective Young's modulus, Poisson ratio, and shear modulus. Next, for our second example, we have a cell with growing crack damage. Elastic modulus for matrix material is 2 gigapascal. Crack starts growing from the center of the plate, and it grows from 0 length to the width of the plate. The effective property are being monitored during the crack growth. The numerical result is then compared with analytical solution, and good agreement can be seen between numerical solution and analytical solution. During this presentation, we introduced the method of modeling periodic microstructured material using ordinary state-based peridynamics. Then we verified our approach, and very good results are being observed. Next, we can further investigate different damage types and their influence on the effective material property of the unit cell. Finally, I would like to thank you for your time. Bye.